Alright, hello and welcome to the electron drift velocity lecture. First thing we're going to do is we're going to define a couple of variables, and we're going to talk a little bit about what makes a good conductor a good conductor. So the properties of a good conductor. Here we have we're going to talk a little bit about what is a good conductor. So good conductors are metals, of course, and those metals are composed of what we call a sea of electrons. So if this is my wire, and inside that wire I have little positive central cores. Now these are protons, and these protons of course are surrounded by electrons, and that's going to be important a little bit later on because the electrons will be bouncing off of these things. In a good conductor, the sea of electrons, there are available little negative electrons that can move, and that's very important because if you don't have electrons that can move, then you can't conduct electricity. So we are going to define our very first variable, which is what we call Ne. The Ne is what we call the number of mobile charge carriers per a unit volume. So, what does that mean exactly? Well, when you have a metal that has a lot of mobile charge carriers, lots of electrons that are free to move about, then you can conduct electricity a lot easier because it is those mobile charge carriers that are moving, right? And we know those mobile charge carriers to be electrons, but they didn't know that always. It took several experiments to figure that out. One of them, of course, is the J.J. Thomson discovers the electron and develops what is known as the plum pudding model. And then there's another experiment by Stallworth and Holman that they took a very large conductor, such as the one that we have here, and they pushed this thing. They shoved it. So they applied a force to this large mobile charge carrier, and they pushed it in, let's say, this direction. And what they found was that when they shoved it, the positive charges moved with it and the negative charges stayed behind. So what does that mean? This side over here acquired a net positive charge because it moved with the conductor. And then, of course, the side on the other side, this side over here, that acquired a net negative charge. And that proved to them that the negative charges, the inertia of the negative charges, stayed behind while the whole thing moved to the right. So this whole thing moves to the right, and then the negative charges stay behind. So we have our Ne from before, which represents the number of mobile charge carriers per a unit volume. And we can change that value by either increasing the size of our object or by increasing the number of mobile charge carriers that are there by using a different metal. So silver's got a good number of mobile charge carriers. Gold has a good number of mobile charge carriers. Copper has a good number of mobile charge carriers. And the more number of mobile charge carriers I have, the better I can conduct the electricity. Exactly what does that mean? Well, that means that back in our wire, the wire's a little bit bigger this time, we have more, here's our positive central cores, we have more negative charges that can move around. So if I have a high Ne, I've got a lot of these negative charges that can move around, and if I've got a low Ne, then I don't have a lot of these negative charges that can move around. So the more of these negative guys that we got, the better off we're going to be. So now we're going to define two more terms. The first one is IE, which is the number of electrons that pass a given cross-section of wire in a second. And the other one is capital NE, which is the number of electrons that pass a given cross-section of wire. So again, if I want to take the IE and the NE and put those in mathematical terms, what I would say then is that the IE is equal to NE divided by time. Or I could then conversely find the total number of electrons that pass a given cross-section of wire as capital NE is then going to be equal to the number of electrons that pass a given cross-section of wire per second times however long that is, times time. So what exactly does this look like? Well, here's our wire now. It is this long circular kind of thing. And inside our wire we have our positive cores. There they are. And then I'm going to just skip a space because I want to try to illustrate something. And then attached to those we have our negative charges. And so the cross-section of wire that we are interested in then is going to be, let's say, this section right here. And I can make it bigger or I can make it smaller. So the section of wire that we are going to choose is going to be that blue section, and we are going to make it delta X thick. Eventually you can surmise that eventually we'll make it dx thick. Delta X just means that it has some width to it. We don't really care what the width is. It could be a centimeter, it could be a meter, it could be, I don't know, as big as an apple. We don't know, and we really kind of don't care. All we know is that there is going to be this delta X there, and that these little electron guys are going to pass through it. And so they're going to come, they're going to start over here, and then they're going to start to flow in this direction. And we're going to be concerned with how fast they're flowing, and we can figure that out, and that's pretty interesting. So you may remember that the title of this lecture was The Drift Velocity of the Sea of Electrons. So we're going to start getting into that now. We want to remember that the velocity, we're going to call that the drift velocity, is equal to our change in x over our change in time. So what was our x? Well, if you recall, our x was this cross-section of area in the wire, which is right here, and it was a thickness of delta x thick. So we could say then that delta x is equal to the drift velocity times time. So we're going to then define yet another term, which is one that you're probably very aware of or used to, and that is volume. And the volume then is going to be equal to the area of the wire times delta X. The volume of electron C that moves is equal to the area of the wire times how far that volume moves, or that sea of electron moves. So that being said, we'll shrink our volume here and we'll kind of push it off to the side. What we're going to do now is we're going to take the delta X from up here, and we're going to simply plug it in to right here. So here we go. Then we would say that our volume, capital V, is equal to the area of the wire times the drift velocity times the time. That is the volume of electrons that move through there. Now that we know the volume of electrons that move through there, what we're going to do is we are going to figure out, well, how many electrons is that exactly? What is that number of electrons? So think back in our minds to the lowercase n sub e. The lowercase n sub e was the number of mobile charge carriers per a unit of volume. Well, now we have that volume. So we're going to take that n sub e and we're going to multiply it by the volume, and we're going to be left with just the total number of electrons. And then again, we can now expand this because we wanted to include our drift velocity. We're going to expand this now to say that NE is going to be equal to lowercase n sub e, the number of mobile charge carriers per unit volume, times that volume expressed in terms of our drift velocity, which is going to be the red equation up there. And that is now going to be the area of our wire times the drift velocity times the time. Still continuing on now, we are going to take this even one step further, and we're going to now find this in terms of I sub e. So remember, I sub e is equal to n sub e over time, and we now know that n sub e is equal to n e a v d t, and then I'm going to divide that by my t, and those two t's are going to cancel out. Bye-bye. And so you're left with the IE is equal to this n sub e a v d. So again, we're left with the question of how do I find the drift velocity? Well, remember that any velocity is equal to the initial velocity plus the acceleration times time. So what is going to accelerate our objects through the wire? Well, remember that the acceleration of any object is equal to the force on that object divided by the mass of the object. Well, the mass that we're going to use here is going to be the mass of an electron. Now, what would supply the force for a charge in a wire? That's right. It's going to be the electric field. So, here is my wire again. Boom. Here it is. And on one side of the wire, I am going to accumulate positive charges. Those positive charges are going to create an electric field that points in this direction. And that electric field is going to motivate positive charges to move from the left side to the right side. It's going to be a force. And the force on any positive charge is related to the electric field, the force on any charge for that matter. The electric force is equal to the size of the electric field times the size of the charge. So, that being said, we can now start to put different pieces together here. So, let's go ahead and figure that out. The acceleration then is going to be equal to E times Q over M, where Q and M are properties of the electron. They're just part of the electron. The electron has a certain charge and it has a certain mass. So we have that the drift velocity is equal to the initial velocity plus the acceleration times time. And I now can say that the acceleration is equal to force over mass, and that force is going to be equal to E times Q over M. So what I'm going to do is I'm going to just kind of put these all together here, and what we would say is that the drift velocity is equal to the initial velocity plus my acceleration, which is now E Q over M times time. So what we have to do now is we have to think a little bit about what is going on in the wire. What is going on in that wire? So again, here's my wire, and my wire has these positive cores in there. And again, we're going to say that there is an electric field that has been established external to the system that is pointing in this general direction. And so my positive charges are going to start on this side, and they're going to generally meander their way over to this way. But what happens, right? So here comes our little electron. Here he is. and he's going to come in because he's feeling a force, and he's going to hit this central core and stop. And then he's going to bounce and kind of come up this way. And he hits this one, and he stops again. And then he bounces off, and maybe he finds a way through. And then he hits another one, and he bounces off, and he hits another one, and maybe he finds a way through over here, and then he hits this one, and maybe he bounces all the way back to here. And then he comes up here, and then he comes on this way, hits this one, and finally finds his way through that conductor. Well, every time that he hits one of these central cores here, he stops. So we're going to go ahead and say that his initial velocity then is 0. And we're also going to say that the amount of time that he accelerates for is dependent upon how densely packed those positive cores are. So that time is a property of the metal, and instead of calling it T, we're going to call it tau. So what does that look like? That looks like the drift velocity is equal to E Q over M times tau. So move it over there so you guys can see it. So we want to keep in mind that some of these things are properties of the metal, because that's going to be important a little bit later on. We can't change the value of Q, that's always the same. We can't change the value of M, that's always the same. And tau is a property of the metal. So let's see how this is going to pan out. So now we know that the drift velocity is equal to the strength of the magnetic field times the charge divided by the mass times tau. And what we're going to do now is we're going to take that and we're going to put it into our old equation where IE is equal to N sub E times A times V sub D. So again, we want to use this 2 and put them together. So we're going to take the V sub D from over here, and we're going to put it right in there, and you kind of get a look at what it's going to look like. That's a mess. So let's go ahead and rewrite it. Let's use black. And so what we find then is that the I sub E is equal to NE, the number of mobile charge carriers per unit volume, times the area, times E Q over M times tau. So this equation represents the number of electrons that go through a cross-sectional area of wire per second. But we don't really care about the number of electrons per se. What we really care about is the overall charge. So what I'm going to do now is I'm going to take both sides of this equation here, and I'm going to multiply them by Q. So I put a Q over here, and I put a Q over here. And then what I'm left with then is the charge that's flowing through that wire. The charge that's flowing through that wire is a little different story because it's actually different than the number of electrons, which is odd. The number of the charge that flows through the wire is a little bit different than the actual number of electrons. The charge that flows through the wire, we define that as current, so I is current, and that is the rate of charge for some amount of time. And that rate of charge then, in terms of electrons, is going to be our I equals our NEA Q squared over M times E and tau. So what we find is that NE, Q squared over M, and tau are all properties of the specific conductor that we're using. If it's gold, it's one value. If it's silver, it's a different value. And so what we're going to do is we're going to define yet another term, And the new term is going to be called sigma, which is the conductivity. And sigma is equal to then N E Q squared over M times tau. And that is specific to the type of conductor that you're using. So then we would say that the current is going to be I equals sigma times the E field.